Hello, I'm Anna Mackay and today we're looking at algebraic expansion and factorization. Let's refresh our memories on things like perfect squares and difference of two squares. So as you know here, this is one version where we've got the a and the b terms. Each of them are squared, and the middle term, there are two lots of a multiplied by b. If it's a difference here, the subtract, notice the subtract is in front of this second term, because when you square the b, those two negatives cancel out to make the positive b squared. And this one here, we've got the a plus b, and the a take b gives us a squared take b squared. So this one is the difference of two squares, and these two are perfect squares. So they're going to come in handy for these solving this and then moving on to exponential ones down the track. Another refresher here, what would this be equal to? Your index laws should tell you that this is equal to 3x, and then you multiply that by 2. So you're multiplying the powers. You don't raise it, so it's not 3x to the power of 2. It's not squared like that. And that is equal to 3 to the power of 2x. What about the second one here? That's equivalent to 3 to the power of 2 multiplied by x, which again is going to give you 3 to the power of 2x. So we're seeing that those two give us the same answer, and that's going to come in handy when we are manipulating some things like this down the track. So if you get 3 to the power of 2x, essentially you know that it could split into either of those two versions. And this one here, we would have 3 squared to the power of x. So if you ever need to split that 9 or a square number, a perfect number, square number, yes, that's right, you can do that, because that would also be the same as 3 to the power of 2x. So another version of that again, all different things to be on the lookout for. Let's do some examples. First of all, expansion. If you're asked to expand and simplify this, you're going to use your knowledge of FOIL, or first, outers, inners, lasts, to expand this. You'll get quicker, and feel free to start heading towards the expansion straight away. I'm going to show every step to start off with. So we're multiplying these first terms. We've got 2 to the power of x multiplied by 2 to the power of x. As I said, I'm going to write all this out to start with. The next, we've got 2 to the power of x times by 1. I'll leave that as that. Next, 3 multiplied by 2x, and then 3 multiplied by 1. So let's look at it bit by bit. This first section here, they are the same base and they're being multiplied together, so we add the powers. We've got x plus x. Please note that it is not 4x squared or anything like that. You do not multiply the 2 and the 2 together. The next one here is going to stay as 2x, but let's also have a look. This is 2x, 2 to the power of x, sorry, and this is 2 to the power of x. So there's one lot of it here and 3 lots of it here. So we're actually going to collect like terms by adding them together to give you 4 lots of 2 to the power of x. That's going to take a while to get your head around, but that's the skill that you're going to need for doing this type of maths. And can we go any further here? Let's have a look at that 4. 4 is 2 squared. And most things here are in base 2, so let's see if that will help us at all. Our final step to simplify things here, I'm even going to make this into 4 to the power of x, using that 2 to the power of 2. And here, look, we've got the same base again, so we're going to add the powers. So we're keeping the base of 2, and we've got, my apologies, that one there should be a 2. We've got 2 to the power of 2 plus x plus 3. So we've expanded and simplified there. Okay, next, expanding and simplifying this one. So we've just got one term out the front, so I'm going to take it one at a time. I'm going to show you every step, x to the power of negative a half, and because they're the same base, we're eventually going to add the powers, but I'm going to write them all out. Next, x to the power of negative a half, multiplied by 2x to the power of a half, and the third one, putting the subtract sign there, x to the power of negative a half multiplied by 3 to the power of, well, 3x to the power of negative a half. Okay, any like terms or anything we can collect here? So we've got the same base here, so we're going to add the powers Negative a half plus 3 on 2 brings us to 1. Next, we've got here the same base, so we can add the powers, but we keep that 2 out the front, the coefficient there. And then we've got the power of a half, power of negative a half and a power of a half, so that comes out to 0. And over here, we've got the 3 out the front, and then you're adding those powers to give you negative 1. Let's tidy that up a little. X to the power of 1 is just x. Anything to the power of 0 is 1, so that means we're just going to have a 2 there, and let's tidy that up to be 3 on x. So that's that one. Expanding and simplifying here. So we've got a perfect square. So my advice is, think about the separate sections. The first term you square, then you've got the end term that you square, and in the middle you've got 2 lots of the other 2 together. So I'm going to write it with brackets. Simplifying further here, with this first term you multiply the powers together. They're sitting on the same level technically. It's not raised to the power of 2. So we have 7 to the power of 2x plus 2. Now what's going to happen here? We've got the same base, so we're going to add the powers. X plus negative x leaves us with no x. So that we've now got 7 to the power of 0. And the last section here, 7 to the power of negative 2x. Please don't put the negatives, say, there or anything like that. That wouldn't be accurate. And just tidying up that 2 there. Again, be on the lookout here. You cannot collect this together because you see the same base of 7 and you think you could subtract the powers. You can't do that. Only when it's being multiplied together, not when they're being added. Factorizing now. So going back the other way. So you need to look for common factors. That's the most common thing to look for. So you can see on the second term you've got 2n. So you might be thinking to yourself, I need to somehow break this up so that I've got a 2n by itself. Well, there's powers being added there. So taking the rule in reverse, if you had the same base, you could add the powers. Therefore, if you've got an add, split them and put it into the same base. So that's the technique. Now we can take out a common factor of 2n, and seeing what we're left with in each term, please make sure you put the plus 1 here. Don't think you've taken that out so there's nothing left over. If you were to re-expand out the brackets, you need to have the 1 there so it gets multiplied with the 2n. And therefore tidying up, because what's in the brackets is actually just a number. You could put a multiply sign or leave it with the bracket. Next one. So we're looking for a common factor. 8 should spring to mind as something base 2. So we've got 2 cubed. So then you'll be thinking back to this one going, all right, I need to look for a common factor. So I need to split this so I do have a 2 cubed. Because the powers are being added, that means we can make them a multiply with the bases. Then take out a common factor of 2 cubed, see what's left over, make sure you write the plus 1 there. We could tidy that up again, turn 2 cubed back into 8. Factorizing this. So you've got base 2, and you might be thinking to yourself, okay, probably a 2 to the power of 2n could be common. How could I split that so that I get a 2 to the power of 2n? So that last term is this, and you're saying to yourself, okay, I want 2n, but what else do I have to do? Now, don't think, okay, there's 2n there, I want 1 more n, so I'm going to put a 1 here. No, because that would be 2n plus 1. You want 1 more n, so you need to put an n there. And now you can take out a common factor of 2n and write what's left over from each term. Next, this one. You might think to yourself, well, 4s and 9s, that's 2 squared and that's 3 squared. They're not the same base. This is now where you need to recognize one of those special products. This is dots. This is a difference of 2 squares. So you're going to head towards brackets, like 2 sets of brackets. You might like to think of it like this to start with though. 9 is 3 squared and 4 is, well, it's like this. Now remember, way back on the first slide we said that 2x squared is the same as 2 squared x. So that's how you might think of it to start with, but feel free to write it in this form because then you get the square in the second position and that might help you recognize that it's difference of two squares. So you'd set up your brackets, one's a plus, one's a minus, and you look at the first term and then you put it in each position. That's how you do that one. Next, this, factorizing now. So again, there's no common factors that are floating around here. Be on the lookout for a special product. Have we got squares on each end with the 9 and the 4? So it's probably a perfect square. But how to write that so that we can see that a bit more closely? So the first term, there's a square. If we think of it as 3x, remember that from the very first slide. And if you're not sure, go back and think about the 3 different ways that we wrote that. The end term, 2 squared is 4. And then in the middle, I like to think of it, it's 2 lots of each of those terms. So let's check that they fit in there. Does that make our middle term? Yes, it does. That 2 and that 2 multiplied together give you the 4. And so that's another way of writing that middle term. Then factorizing that in brackets like this, all squared, is it a positive or a negative, like an add or a subtract? It's an add, and then you put each of those terms in there. Phew! So that's the end of this video. Later on we go into factorizing other trinomials, but the next video is exponential equations. Thank you.